All right, so let's get started. So the last talk will be by Chi-Young Kang on robust bounds for welfare analysis. Please.
Excellent. Well, thank you everyone for making it to the last talk of EC. I'm very excited to be presenting this work called Robust Bounds for Welfare Analysis. My name is Ziyang. This is co-authored with Shosh Vasserman. So let me begin with a really simple question. The question is as follows. You observe this demand curve that you see on the left-hand side. And the question is, how much are consumers hurt when the price increases from P0 to P1? Right? So most of you have heard some variant of this problem before. If you've ever taken Econ 101, you will know that the formula for the change in consumer surplus is going to be given by the area between the demand curve sandwiched between the two prices. The problem with this type of analysis is that the demand curve dp here is usually not observed. Right? So for example, we may only observe 2 points of the demand curve. Those are the 2 points in blue that you see. And this is given by P0, Q0 and P1, Q1. Right? So this is sort of a twist on the canonical problem of estimating change in consumer welfare. I want to argue that not only is this question canonical, it's also relevant for a lot of policy questions. So for example, here's a question about evaluating the deadweight loss of the Trump tariffs. These were a sequence of tariffs implemented from throughout the course of 2018. And the question is, how much did the 2018 Trump tariffs hurt American consumers? This is a widely studied question. There's a lot of work that we cite here written about the subject. But this sort of policy question is very related to what we study in the paper. So instead of observing the entire demand curve for each good, really what you observe is just 2 points along the demand curve, right? So you observe P0, Q0, and that's the point before the tariff was imposed. And you observe the point P1, Q1, which is the point after the tariff was imposed. You know exactly how much tariff was imposed. You see these 2 points, you want to measure the deadweight loss, which is equal to the area of the shaded region that you see on this demand curve. So what is the standard approach that this empirical literature takes? Well, the standard approach takes 2 steps. The first step is to estimate this demand curve. So you assume some functional form for the demand curve. Say I assume that the demand curve is linear, and that this demand curve passes through these 2 points. Right? So you find the linear interpolation between these 2 points. And the second step is assuming that this is the actual demand curve, we compute the change in consumer surplus using the formula that I gave you on the previous slide. So you integrate this interpolation and you figure out what the change in consumer surplus is. Right? So this argument works when these 2 points are very close together. You can argue through a Taylor approximation that this approximates the true change in consumer surplus. But in the case of the Trump tariffs on some goods were as large as 20%. You no longer can use this Taylor approximation argument to say that this is close to the actual change in consumer surplus. Beyond just this example of tariffs, many papers in economics have a similar structure. And our point here in this paper is that measuring welfare requires taking a stance on what the demand curve looks like at unobserved points. Right? So often we assume functional forms, such as a linear demand curve in the previous slide, just for the sake of convenience. But in this paper, we really want to engage researchers. We want to challenge researchers by asking whether there's a more principled way to engage with assumptions and to evaluate the change in welfare. And so what we do in this paper is that instead of interpolating between these 2 points to get a welfare estimate, we establish welfare bounds that hold for a family of demand curves. These bounds are robust in the sense that they give the best case and worst case welfare estimates that are consistent with whatever sort of family of economic assumptions that we consider. And these bounds are also simple in the sense that they lead to closed form expressions for what the best case and worst case welfare estimates will be. Our bounds shed light on welfare implications of commonly used demand curves. So this was not the intention when we first started out this project, but rather this was a product of the kind of results that we got. Right? So we characterized the best case and worst case welfare estimates, and then we realized that the demand curves achieving these bounds were actually demand curves that people were using commonly in different literatures. So for example, we found out that the constant elasticity of substitution, or CES, demand curve, by using that demand curve, to interpolate between these 2 points, that yields the smallest welfare estimate among all possible interpolations under the assumption that the demand curve satisfies Marshall's second law, which is sort of the most commonly imposed assumption in the trade literature, in the literature where people consider all these welfare effects of tariffs, for instance. In addition to deriving all these theoretical results, theoretical bounds, we also have an applied section of the paper where we show how these bounds can be applied to a variety of settings across different literature, so including tariffs. We also looked at energy subsidies, pensions, as well as the classic problem of income taxation. Okay, so diving immediately into the model, just to make this very clear, our setting is a setting where we do not observe the demand curve, but we observe these 2 points. Of course, there are natural generalizations. You could imagine having access to finitely many points on the demand curve. For simplicity, we stick to 2 points. And the question we're interested in is we want to evaluate, we want to bound the change in consumer surplus. Right? So what that looks like is the change in consumer surplus is going to be the sum of areas A and B. Area A is just going to be the area of this rectangle. That's going to be very easy to compute once you know P0, Q0, and P1, Q1. The much more challenging thing to bound is area B, because that requires some dependence on the demand curve that you do not observe. Right? So the entire purpose of our exercise is to bound area B. And many of you will be thinking right now that, of course, the demand curve is decreasing. We can already establish some simple bounds on this change in welfare, and you are entirely correct, right? So a naive upper bound on this area B, assuming that the demand curve is decreasing, will be given by this red line, right? That's the largest possible decreasing curve that you could use to connect these 2 points, P0, Q0, and P1, Q1. That gives you a bound on area A. And in the other direction, you could also draw this green curve. That's the smallest possible decreasing demand curve that passes through these 2 points, right? So what these extremal demand curves show is that even under minimal assumptions, you can already derive some meaningful bounds on area B, and in so doing, you can compute bounds on consumer surplus. Now, one pushback against this minimal assumption is that these bounds are attained only when the elasticity of the demand curve is equal to 0 or negative infinity almost everywhere. Right? So if you go to literature, there's a huge literature in economics estimating elasticities. These elasticities range from minus 0.3 to minus 18, minus 19. But that's across different markets. Within each market, you often get a much smaller range. And so a natural question to ask is, how do you translate from these elasticity ranges that you get for each particular market to bounding the change in consumer surplus for that particular market? Right? So a very natural way to capture that is with this additional assumption highlighted here in red. So we observe 2 points on the demand curve, but we also know that elasticity between these 2 points lie within some interval, epsilon lower bar and epsilon upper bar. So our goal here is to use this additional information to help obtain a tighter bound on the change in consumer surplus. Before I state the result, just a piece of terminology here. So I'm going to call things either one-piece interpolations or two-piece interpolations. One-piece interpolations are things like what you see on the left. So when I say something is a one-piece linear interpolation, I'm literally interpolating between these 2 points with a one-piece function that's a linear function. And if I call it a two-piece linear interpolation, I'm basically saying that I connect, I have a one-piece interpolation between P1, Q1 and an auxiliary point in green, and then take another one-piece interpolation from that point to P0, Q0. Okay, so the theorem that we have here in this particular assumption of elasticity ranging from epsilon lower bar to epsilon upper bar is that the upper and lower bounds for the change in consumer surplus are attained by two-piece CES, constant elasticity of substitution demand curves. Right? So what that looks like is going to be something like what you see. So the upper bound is going to be attained by this red demand curve that is a CS interpolation to some auxiliary point in red, and then another CS interpolation to P0Q0. And so is the green lower extremal demand curve, right? So that's also going to be a two-piece CS interpolation. And this sort of generalizes the simple example that you saw. So if we took the limit where epsilon upper bar goes to 0 and epsilon lower bar goes to negative infinity, you get back this, this rectangle that you see on the right-hand side. The proof is actually very simple, but what we want to highlight here is that is exactly this first point. So the way we prove this is we define the partial order on demand curves. So we order these demand curves by mean preserving spreads of elasticity between P0 and P1. But really what surprised us was how similar this problem is to the problem of Bayesian persuasion. So there's a direct connection between our exercise here and the question of Bayesian persuasion that the literature in theoretical economics considers. Right? So in some sense, once you write this down and formalize this as an optimization problem, we show in the paper that this problem is equivalent to, in some sense, to a classic Bayesian persuasion problem. And finally, the change in consumer surplus is going to be monotone in this partial order, and that's how we use that's what we use to get this result that the upper and lower bounds are attained by two PCS demand curves. Right, so a few remarks about this result. This result allows these bounds to be easily computed. That's because I know the functional form of the CS interpolation, so I can compute these upper bounds and lower bounds in closed form. And finally, this is very much related to a sufficient statistics approach in applied economics, where they think about mapping from local elasticity estimates to local welfare estimates. By contrast, our approach maps from global elasticity bounds to global welfare bounds. This is something we comment more in the paper. So beyond this assumption of saying, elasticity between these 2 points lies between epsilon lower bar and epsilon higher bar, we also consider other assumptions that are commonly imposed in the literature. So this is a list of the assumptions that we consider. We consider these assumptions individually. We consider combinations of these assumptions in the paper. And we have corresponding results for each of these assumptions. The one thing I would like to point out from this slide and the next is that many of these interpolations are commonly used functional forms. And so there's a very real sense in which, when the literature says, let's just assume that there's that the demand curve is linear, or let's linearly interpolate between these 2 points, we're actually achieving the highest possible welfare estimate or lowest possible welfare estimate within a family of demand curves. Okay, so let's go back to the question that I started out with and look at the effects of the Trump tariffs on deadweight loss, right? So by way of background, this is a sequence of tariffs that were introduced over the course of 2018. So this graph, which we took from a paper by Amity et al., shows exactly, it shows on average the size of the tariffs that were introduced in each month of 2018. Right, so if we just look at a single product that was affected by this sequence of tariffs, so let's just look at photosensitive diodes that were imported from China. This is a plot of deadweight loss in millions of dollars against what you see on the horizontal axis, which is each month, right? So presumably here, a large tariff was introduced in August of 2018, and so that's why you see that the deadweight loss suddenly jumps from about 1.5 to something closer to 6 on average, right? So these plots that you see assume a linear interpolation. So that's what the authors of the paper consider. But you could also consider other functional forms. These other functional forms are sort of extremal demand curves that we show for different families. So if you use an exponential interpolation instead of an a linear interpolation, you get actually a much lower estimate of deadweight loss in millions of dollars. You can do this for more functional forms. And you can also do this for the elasticity assumptions that we impose, right? So the lower bound that we ended up with was when we imposed Marshall's second law, which is, again, a commonly imposed assumption in the trade literature. And so imposing this assumption yields a lower bound on deadweight loss that is $12.6 billion. By contrast, the tariff revenue that was gained over the course of 2018 is $15.6 billion, right? So there's a gap between how much it hurt consumers, which is $12.6 billion, and how much the government was able to extract in terms of revenue, which is $15.6 billion. And the linear interpolation that was applied in the paper yields a deadweight loss estimate of $16.8 billion, right? So how can you use our results to say something about these estimates? So one question you might ask is whether there's a sense in which the $16.8 billion might be an overestimate. And using our results, we show that the answer is yes, if we expected the change in elasticity down the demand curve to be small. And also, if we expected the demand curve to be convex, then $16.8 billion is actually an upper bound because the upper bound for convex demand curves is attained by a linear interpolation. By contrast, you might also ask whether there's a sense in which the $16.8 billion might be an underestimate. And using our results again, you can show that the answer is yes, if we expect the change in elasticity down the demand curve to be large. So let me conclude. The main contribution of this paper is that we develop a framework for bounding welfare based on principled economic reasoning. And these bounds are robust and often simple. The bounds themselves emphasize assumptions based on economic primitives. So for instance, we have assumptions on empirical objects, such as elasticities that are measured. And we also have assumptions on theoretical objects, which are things that look more like curvature of demand curves that are often used by theoretical and empirical researchers alike. Right? And finally, we're able to interpret these common functional form assumptions through their curvatures. Right. Very good. So that brings me to the end of my talk. Thank you very much for your attention.
So thanks for the nice talk. Can you hear me? Do you have questions? Don't take it personal. It's the last talk. Yeah, we have one.
16 billion, is it like compared to like the order of magnitude of this economy? How much is it? Like losing 16 billion, what is the order of magnitude of how much money is involved in this exports?
So the question is how big $16 billion is relative to the magnitude of these imports. I don't have that number offhand, unfortunately. But these tariffs are large in the sense that typically they're probably, they're large in the sense of the graph. I guess there's no. Well, so these tariffs are large, as you can see when they were imposed over time. There's also the 3 papers that we cited, and those have answers about the magnitudes.
Do we have a question in the virtual space? Or I think there's maybe only the share. Do you have a question? No. So maybe I have one question. So I mean, I'm not very familiar with the topic, but could you think of other techniques like getting additional samples or some information about the gradient at these points? Would that be something that could help? Was that considered?
Yeah. So so in terms of gradients, elasticity is a measure of how quickly or how steeply a demand curve changes. So that captures some notion of gradient. In respect of additional samples, we do that extension in a paper. But this sort of approach also allows you to quantify what the value of additional sampling is, for instance, because you get you are able to derive upper and lower bounds for a given sample size. So. All right, that was the long answer. Yeah. The short answer is yes.
Cool, thanks. Yeah. All right, so let's thank Chi Young and all the speakers of the session.